So let me now talk about a first application of these models in some detail, and that is to the parsing problem, but in particular to an approach called re-ranking. We'll talk about how to re-rank the parses, or rather the n-best parses, from an existing history-based or probabilistic parser. So in re-ranking approaches, we're basically going to do the following. We'll use some baseline parser. In particular, this might be a lexicalized PCFG, for example, which we know is quite a good model for parsing. We're going to use a baseline parser to produce its top n parses for each sentence in training or test data. So n, for example, might be 25 or 50 or 100, and I'm assuming that I have some way of finding the top 25 or top 50 or top 100 most probable parses under the lexicalized PCFG model. In fact, there are variants of the kind of dynamic programming algorithms we saw earlier in the class which will do precisely this. They will return the top n most likely parses. Now, if you think about that, we can visualize this as following. We have a sentence, and we generate a bunch of parses, say the top 50 most probable parses under the lexicalized PCFG. Even if the first or the most likely parse under the PCFG isn't the correct one, there's a good chance that one of these 100 parses will be correct. And there's an even better chance that one of those 100 parses will actually be much, much better than this single best parse. So in the particular experiments I'll describe a little later, we actually generated about 25 parses on average for our 40,000 training sentences. This gave us about 1 million training parses if you consider all possible members of Gen for all possible sentences seen in the training data. So our supervised data is going to look like sentence tree pairs, and we can do a couple of things there. We can either take yi to be the true tree bank parse for that sentence, or we could take yi to be the member of this function gen, which is closest to the tree bank parse under, for example, precision and recall. That's a minor detail. Just assume that we have some way from our tree bank of choosing one of these members of gen x as being the label, the correct parse for this particular input. Now let's talk about the representation f, the feature vector mapping we used. So the critical idea is, in these re-ranking approaches, we have a function f that takes an entire tree as input and returns some feature vector. So maybe some sequence of features. And each of these features is going to be a function mapping a tree to a real value. And critically, we're really in a position where we can define any features we could think of. So if we think back to those examples of parallelism and coordination, things like bars in New York and pubs in London, then we could, for example, have a feature that identifies the fact that this particular structure is a parallel coordination structure. And we could, for example, have a feature which counts the number of parallel coordination structures we have within a parse tree, or a feature which counts the number of non-parallel features, structures we have within a parse tree. By introducing features which track this kind of, or the frequencies of these parallel versus non-parallel structures, our model can learn to prefer parallel versus non-parallel structures. Here are some other features, actually some features used. Another very useful feature is actually the log probability of xy under our baseline model. Remember, this is a lexicalized PCFG. And so we can take the probability. It's often slightly better to take the log of that probability, and that might be our first feature. This basically gives us a default ranking. So at the very least, our re-ranking model should do as well as the lexicalized PCFG, because it has this information from the probabilities under the PCFG. Here's another potential feature. This is a 0-1 feature, an indicator function, very similar to the indicator functions we've seen on log linear models earlier. This is 1 if the XY pair contains a particular context-free rule. For example, this entire context-free rule here. Let me describe some features used in a paper I wrote with Terry Koo back in 2005. And throughout this, I'll use this quite complicated rule. VP goes to prepositional phrase, VBD, NP, NP, S bar as the example rule. And the features, as we'll see, are generally oriented in some sense around context-free rules like this one. So the first set of features we included in the re-ranking model were features which considered individual entire rules. So for example, we might have one feature which counts the number of times I've seen this particular rule within the tree. Now, interestingly, the lexicalized PCFG we were using broke these larger rules down into smaller ones, roughly speaking, through binarization, through this process where we take this rule and we might somehow binarize it by introducing some intermediate non-terminals. Okay, so the underlying lexicalized PCFG was in something close to Chomsky normal form, and so it didn't really have parameters corresponding to entire large rules like this one. In the re-ranking model, we actually added in features corresponding to the entire rules. The motivation for that is that some of these rules are very important, and while this Chomsky normal form grammar is very useful in reducing the number of parameters in the model, it does make some assumptions which miss some important properties concerning the frequencies of entire context-free rules. So we added features like this, and they're quite useful. Here's another feature centered around this particular rule example, which captures something which the lexicalized PCFG was missing. And these are sort of bigram features within rules. And these are adjacent pairs of non-terminals to the left and right of the head. So in this particular rule, we're going to see the following bigrams. We're going to see 1, 2, 3 to the right. So in each case we have the non-terminal, this is a VP up here, and we have a pair of consecutive non-terminals, NP, NP. So that's where this particular feature comes from. Another feature would look at the fact we again have something to the right of the head of this rule. So the VBD, by the way, is the head of this rule. And this would look at the fact that I have a VP, an NP, and an S bar to the right. Finally, I have again a rightwards feature with VP, S bar, stop, acknowledging that stop is the final component of this rule. And I have leftward bigram over here, which is leftward VP prepositional phrase stop. So these features are going to be capturing bigrams within rules, and again, the lexicalized PCFGs we were looking at really missed these features, and so we're introducing new features which again can be useful in disambiguating good from bad parse trees. Here's another example of the type of feature you might include. So we call these grandparent rules, and so these features are not going to be sensitive to just the rule, for example what I've shown here, but also to the non-terminal directly above, an S in this case. So we've essentially introduced a feature corresponding to a larger fragment of this tree. And again, these features are not included within the lexicalized PCFG, and they can be useful in some cases. A minor variant of that idea is to actually include two levels of context-free rules. So the fact we have an S goes to NP VP here, followed by VP being rewritten as this entire rule here. And we could introduce similar features to this for many other two-level rules seen in our training set. So that gives you the basic idea. That's some examples of a few of the features we use in this model. And you can see that the basic idea is to start to introduce features which look at larger fragments of these syntactic structures and which go beyond the kind of features we saw in the simple lexicalized PCFG.